Okay, welcome everybody to the LPL Colloquium series. Today we're visited by Dr. Mike Way from the Goddard Institute for Space Studies in New York City. So Mike got his PhD in 1998 from the University of Missouri at St. Louis, followed by a few years on staff at Princeton. After that, from about 2000 to 2011, Mike was a civil servant at NASA Ames Research Center in the astrophysics branch. So I almost overlapped then with Mike before I spent my time at Ames, but Mike departed before I would have that luxury. And so then Mike headed to New York City to be at the Goddard Institute for Space Studies. Many of you probably know Mike from one of his hats, which is leading the development of the Rocky 3D planetary general circulation model. I was on the telecon where that terrible or amazing acronym was created, and I take no credit or responsibility for that, and I can't even remember what it is most of the time, so Mike will have to tell you. But Mike also wears another hat, which is he's a card-carrying cosmologist, and so has research that spans the biggest things in the universe down to planets, which begs a very important question. Are you more frequently called a cosmetologist or an astrologist? Okay, and with that, I'll turn it over to Mike.
Thank you, Ty. Thank you for hosting me for these couple days here. And sorry, I screwed up on my holidays. I forgot that Monday was a holiday, and I thought I was going to have all these great chats. But thankfully, Daniel made time, so we had a really great chat yesterday. So I'm going to talk about some work we've been doing for a few years on a possible climate history for Venus here. And I'm going to try to connect to some recent spacecraft data and spacecraft, because everybody likes spacecraft, right? They always look cool. And I'm going to show you some really cool pictures of a really old spacecraft that we're still getting data out of, which I find really fun and exciting. And maybe as a teaser to try to get one of my colleagues to come in and give you a talk in much more depth about that particular mission. So this idea that Venus has been habitable has been around for decades. But when you look at the numbers just on the surface, how could this even be possible? Like, if you look at Earth today, we're receiving around 1361 watts per meter squared. If you look at Venus 4.2 billion years ago, we're getting about 1900, which is about 1.4 times what we get today. And of course, today we're getting about twice as much at Venus. And if you think about Earth being at the inner edge of the habitable zone already, this seems like a preposterous idea. But let's look at some different theories of Venus's climate history and see if we can figure out how this might be possible. There's a couple traditional views, and this is the first traditional view that we have for Venus, that it started out as this kind of magma ocean world. Yes, this is a fake image of 55 Cancri, but I got to find something that works, right? We have a magma ocean world, and somehow it ends up into this thing we see today, this Hell House world. And the idea behind this goes back to some work by people like Keiko Himano, and let me see if my laser pointer works without destroying the whole system here. It never works when you want it to. Anyway, Keiko Himano and Lebrun, they have a couple papers from a couple of years ago, which really investigated this. And in those papers, they use some 1D modeling of the atmospheres and over a magma ocean. And in those models, they have these sort of steam atmospheres with some CO2 or N2. It doesn't matter so much. It's the steam that matters. But the idea is in this model is that Venus had this long-lived magma ocean phase of roughly 100 million years. This primordial water was lost through photodissociation. The hydrogen escapes to space, and the oxygen is absorbed by the magma ocean, and you set your redox date for your planet right there. You're done. The planet's been bone dry for 4 billion years. No ocean condensation was ever possible. And the high deuterium to hydrogen ratio that we see, which is about 150 times what it is for Earth, was set from that time. And there's some other supporting works. It goes all the way back to Ingersoll in 69, who had the first sort of hothouse model, and then up to more recent work using a 3D GCM by the LMD group in Paris by Martin Turbet and collaborators. The other traditional view, and this was also supported by the same papers by Himano and Lebrun. It drives me crazy when I read that these people only had one scenario. They had both scenarios in the paper, but people only read half these papers. I don't know why. You read what supports your own hypothesis, I guess. In those papers, they talked about a short-lived magma ocean, somewhere between 1 to 5 million years, something probably what occurred here on Earth. The steam atmosphere condenses out on the surface. When it cools down, boof, your oceans are there. You have some undetermined habitable phase and a few pieces in the literature. It's about a gigayear or less. Sun luminosity increases through time. We all know that. You get into a moist and then a runaway greenhouse state. And the high D/H comes from the loss of those oceans. And it's, again, about 150 times what it is today and transformed into this hell house world. So from a magma ocean state to something resembling Earth to something resembling modern day Venus. And this also goes all the way back to Jim Pollock in 71, Bullock and Grinspoon in 96, and again, these two papers I mentioned before. Okay, so what are the pluses and minuses here? So with the traditional view number one, the nice thing is that it easily explains the present day state. As I said, the hydrogen escapes to space after the photodissociation, oxygen's absorbed in the magma ocean. We never had any volatile cycling. The only question that people always ask is, why does it still have a thick atmosphere? Because, you know, magnetic fields are so important to protect your atmosphere. It has this giant atmosphere. So what happened? Well, maybe magnetic fields aren't that important, or its magnetic field shut off in 1962, just before, you know, Mariner 2 arrived. This sort of habitable scenario has a bit of a problem. It doesn't explain the present day state. And the big question is, where is the oxygen? If you had, you know, you're going to end up with tens or hundreds or thousands of bars of O2, and that's not what we see. We're talking about a world with very, very little oxygen. And that is the real conundrum. And this is even discussed about in the context of exoplanets by some papers by Luger and Barnes, Wordsworth and Pierre-Imbert, and Vicky Meadows also has a paper on this, that there would be worlds with these 1,000 bars of O2 in them, you know, as kind of a biosignature, you know, oh, they lost all their oceans and now it's all sitting in their atmosphere. So that's the big problem with this particular habitable scenario. Where is the oxygen? Where did it go? And we'll see that will come back to haunt us a little bit later. Okay, but was there a steam atmosphere? This is a really nice paper. I'm just showing you one of the plots from it, only part of the plot actually, because it's so big I can't fit it all on these slides, by Dan Bauer and company, retention of water in terrestrial magma oceans and carbon-rich early atmospheres. I would first say there are few compositional constraints on the magma ocean atmosphere. So if we look here at this plot, and we just look at the 30% melt column, the red stuff is CO. So that is one of the more common outcomes, depending on what your redox state is for your magma ocean and how much water you have in the magma ocean, et cetera, things like that. And what you can see here is the blue is the water. And in most cases, there's not that much water. Some cases there's some, but it's by far not even half in any of these scenarios. In some cases, it's CO2 dominated. In this case, here's CO. There's another one, CO and CO2, even some with H2. So I would say we actually don't know what these early magma ocean atmospheres consisted of or consist of because we don't have any constraints. We don't have any idea. We don't know what the redox state of the early magma ocean is. But if you do, let me know. Maybe we can pick one of these and do some modeling. So the stuff that Himano and Turbay have modeled are these atmospheres, as I said, that are mostly CO2 with water vapor. They don't fit any of these models, just so you know. But maybe Da Vinci, which is a mission led out of Goddard that's going to send a probe into the atmosphere and get us all the noble gas isotopes and everything else in the column atmosphere. Maybe it'll help. Or you exoplanet people, maybe you can find us some observations that, if you can find us a magma ocean atmosphere and tell us what's in it, maybe it'll say something about at least that world if it doesn't say anything about our own. Okay. Oh, this side's very busy from this perspective. Okay, so what else do we have here? The other takeaway, I think, is that water is highly soluble in most of these melt scenarios. And I like this paper from Paolo Sossi from 2023, where he says it very nicely. Because the solubility of water remains high relative to that of CO2, steam atmospheres are rare. They may form under moderately oxidizing conditions on telluric bodies, provided sufficiently high H to C ratios prevail. So this idea of the steam atmospheres for the magma ocean are really being put under question, I would say, by these modelers. This is another paper by Maurice and collaborators. He's now at LMD, but he did this work when he was at Rice. showing even more scenarios similar to the Bauer stuff. So as I say here, in other words, we don't have good constraints on the post-accretion atmosphere of Venus or Earth. So it's really hard to say what these magma ocean atmospheres were and how they changed throughout time. That's the big issue we have for early Venus and even early Earth for that matter. Okay, so let's move on to a kind of possible newer view of what Venus might have looked like in a habitable phase, where we have assumed a short-lived magma ocean or some kind of late water delivery if the planet cools down enough for that. A long period of habitability, long meaning more than 1 billion years, take it or leave it. There has to be some kind of volatile cycling or plate tectonics going on, of course. And then there's going to be some kind of transition to the hothouse. And how does that occur? And that goes all the way back to some papers by Jim Pollack, Grinspoon and Bullock, Abe, LeConte, and a few others in our own work here. So is there any evidence of surface liquid water in Venus's history? That's the first question we have to ask. And if yes, then clouds in concert with rotation rate may have played a role in any kind of Venus ancient climate. So this is what we have, traditional evidence. I say traditional evidence of surface liquid water on Venus. When people want to talk about surface liquid water, this is the stuff they cite. I'm not saying it's right. I'm just saying that's what we say, all right? The first is the Pioneer Venus. So when you see PV in my slides, that's Pioneer Venus. That's a picture of Pioneer Venus coming into the atmosphere of Venus back in 1977. Or 78, sorry, where we measured a very high D to H, 150 times Earth's D to H. The only negative is that the H2O loss, type of loss, the time scale of the loss is unknown. So we don't know when it occurred, and we don't know the time scale over which the water loss occurred. There's a paper from Watson in 2007 that says the argon 40 stuff is saying something about plate tectonics and that this number means that there was some kind of water cycling on the planet. It's highly speculative. I don't think most people buy it. The Galileo probe, maybe you don't know this, but did a Venus flyby, Solar Orbiter and Bepi Colombo and all these missions when they fly by Venus, we begged them to turn on their cameras to take pictures of it. And Galileo did this. And there was some evidence from that some of the highlands could be felsic or granitic. That's very speculative, but that's what people believe. If you have granites, maybe you have some water going along with that. And then this nice paper from 1990, and then a reanalysis that was redone in 2019 by Shellnut of the Veneer 8 found what they considered to be a greenstone belt on the surface of Venus in the basaltic plains, which is really strange. But those would also form under some sort of water conditions. And then a more recent work by one of Richard Ernst's students at Carleton, Khwaja et al. From 2020, we're looking at the Magellan radar maps for Venus, and they believe that some of the channel features, they say, look like fluvial erosion, and they have similar morphologies to what we see here on Earth. Is it right? We don't know. The only resolution to at least some of this is going to come from these future missions. So one I've already mentioned, which is Da Vinci, which is going to fly out of Goddard Space Flight Center. Veritas, which is going to fly out of JPL. This is a radar mission, and Envision, which is an ESA-led mission to Venus, which will also have a radar built by JPL also, but also some infrared imaging instruments, which are going to be really interesting. Okay, so let's move on to clouds and then rotation rate. So this is a really interesting and overlooked paper from 1971 by Jim Pollack, who led one of the branches that Mark and I both worked in way back when. But maybe, I don't know, do you ever overlap with Jim?
He was my postdoc in West.
Yeah, oh my God, you're so lucky. Well, he must have been a great guy to work with. A really gifted man. I've not ever heard a negative word about this person. This is the paper I'm talking about from 71 in Icarus, a non-gray calculation of a runaway greenhouse, implications for Venus's past and present. It's a 1D climate model. This is the killer plot from that paper here. And all I want to point to is that this plot is for a model he did with 100% cloud cover. And at 4.5 billion years ago, in his 1D model, he gets a temperature, global mean surface temperature, his 1D model of 290 K with 100% cloud cover. Here's another model where he uses 50% cloud cover and the thing goes runaway. Okay, fine. But he never really explains why he picks 100% cloud cover, but yet he does. But we're going to turn out that that's sort of useful in a way, which is kind of surprising. So it was already known in 71 that if you have a planet very near its host star with 100% cloud cover, you can get temperate conditions on the surface. Okay, then 43 years later, we find a way to get that 100% cloud cover. This goes back to a paper from Jun Young and collaborators at University of Chicago in 2014. Strong dependence of the inner edge of the habitable zone on planetary rotation rate. So these plots are a little complicated, so I won't spend too much time on them, but suffice to say that each one of these colored lines represents different sidereal rotation periods with respect to Earth. So these are a series of models with Earth rotation rate. This is a series of models with Earth rotation rates, but 16 times longer day lengths, 64, 128, and 256. And each one of these data points is a model, a 3D GCM model. They use the NCAR model if anybody's interested. And each one of these mean surface temperature points is also overlaid on what the stellar flux was that they used for that particular run. So here is modern day Earth, basically 1361 in essence. And then we ramp up the insolation. And what you see, first of all, is that for Earth rotation rates, Earth day lengths, these things go runaway pretty quickly. You can't add too much solar insolation before they get too hot and the models basically die. I mean, these aren't in a runaway state because the models can't run runaway state. They can't go that far, but they've died because they're just too hot. But you can see as we increase the length of day, I can ramp up these insolations quite high, and my mean surface temperatures are not going off the charts. And that's all because of the planetary albedo from the clouds. So when you're slowing down the rotation rate of this world, what you're doing is you're weakening the Coriolis force, which is what gives us our 3 Hadley cells in the south and our 3 in the north. When you slow it down quite a lot, you end up with 1 Hadley cell in the north and 1 Hadley cell in the south, similar to what Venus has today. And so what you see is that the slow rotators have really extremely high planetary albedos. And that's the key to keeping that 100% kind of cloud cover that Jim Pollock modeled without any rationale for it in 1971. And this is a nice picture from that Yang paper, one on the left showing rapidly rotating planet with cloud percentage here in different colors. So you can see there's not so many clouds here in some places, whereas when you go to the slowly rotating, in this case, the 128 day length case, here's a substellar point. You end up with this gigantic substellar cloud deck right where the solar insolation is at its strongest. And that's what prevents these planets from getting super hot, just because of the rotation rate changing. Okay, well now the question is, what was its rotation rate? Was it rotating slowly enough or not, right? There are many ways to make a slow retrograde rotator with a small obliquity. I don't have time to go into all these. I can give a lecture just on these 5 schemes. I'm just going to give you their names. One is an impactor. Doesn't surprise anybody here. I know many of you work on impactors. You can figure that out for yourself, but a lot of that work was already done in the late 60s. So there's not much left to do for you. I'm sorry. Something called solid body tidal dissipation, which I'm sure you're aware of. Something more obscure that's been promoted by people like Dobrovolskis and Laskar and their groups. Something called core mantle friction. Atmospheric tides, which we see work really well today on Venus. And even if you have some kind of oceans, you can get ocean tidal dissipation, which is really efficient in some cases. Okay. So assuming that Venus was a slow rotator for much of its history, let's test this Venus habitability hypothesis with those assumptions. And we'll use this model, which Ty mentioned, with this incredibly irritating acronym, which I won't even read out for you. But you can see, this is NASA. And the first thing that my boss did when we put this model together, let's make an acronym, and Ty was there. And we've been cursed with this ever since. So in-house, I call it the R3D model, just to keep it very simple. Anyway, this is a model we developed at the NASA Goddard Institute for Space Studies in New York City. Our model is basically a child of this Model E, which is our parent climate model, which participates in climate change studies. So things like IPCC, CMIP, PLIOMIP, you name it, they've done it. What we did for a few years ago was change some of the capabilities of the model to do more other kinds of diverse atmospheres, basically, because the model is very tuned for modern day. Okay, so what is this model? What we call a full complexity model. It's an atmosphere with 40 layers, a dynamic ocean with 13 layers. It's not a slab ocean, which is what most people are using in the exoplanet community. And there's reasons for that, which I can go to later if people are really interested. We have a land surface model with 6 layers. All these are coupled, of course, through some kind of coupler. The resolution we run at is not super high resolution for those of you that are big GCM people because, well, I got so many other unknowns. What's the point in running the thing at high resolution anyway? This is good enough, and it runs quite a bit faster. And we use a highly flexible third-party reader to transfer scheme called Socrates, which we stole from the UK Met Office because we got one of their graduate students as a postdoc, and he plugged it in for us over a couple months. So we can do a lot of really cool stuff with it. Okay. Let's look at what we did for what kind of things we modeled. So we modeled 5 different kinds of Venuses. One is an arid Venus or a dune world, or pick your favorite science fiction world with no water, but there's some water, where we only put 20 centimeters of water in the soil. That's something that could even be delivered through a late veneer. That's why I put these sort of things there. A 10-meter Venus, that's 10-meter global equivalent layer located in lakes. Basically, again, it's not a lot of water, but all of these scenarios fit within that giant error bars we have on the D to H ratio. A 3 10-meter Venus, that's again 3 10-meter GEL in lakes and oceans. Probably delivered primordial in that case because it's too much water for a late veneer. And then some other scenarios that people just love to use. An aquaplanet scenario with 158-meter deep ocean. And we also did, just for fun, modern day Earth. We just give it a bathtub ocean. Why do I give it this shallow 3 10-meter bathtub ocean? Don't model the full Earth because, well, it comes into equilibrium faster. Instead of running the model for 5 months, I can run it for 1 month, and the ocean comes into equilibrium much more quickly. Okay, so what do those look like? So this is all gobbed together in one big plot. I'm not going to go through everything here, but the numbers are those 5 different scenarios I just showed you. All of these should overlap at the same time period. So we did a few simulations at 4.2 gigayears with different kinds of rotation rates. Again, I won't go into that too much, but if I go to like the 2.9 gigayear scenario, you can see that for all the scenarios, my global mean surface temperatures are not fluctuating that much. They're very near that Pollock value that we saw before. If I go already all the way to about 0.7 gigayears, it's the same. So what you see here is really interesting. So remember that early traditional view was that the solar luminosity increasing through time. So again, here we are gigayears ago, 4, 3, 2, 1. And then at the top, I'm giving you what the solar insolation is as compared to Earth today. You can see, even though we've increased the solar insolation by quite a lot, the mean surface temperatures are not changing that much. So solar insolation, if you have a habitable world like Venus, it's not the increase in solar insolation through time that's going to drive the planet into a runaway state. It's going to be something else, because that cloud albedo feedback in these models is very, very effective. Even up to present day. Here we are getting twice what we get at Earth, and it's still working pretty well for most scenarios. Now, if we condense that all down into one simple plot, you can see we have this kind of magma ocean phase, a cool early Venus. I copied this from the Earth literature because there was this idea many years ago before the LHB started falling out of favor. There was a cool early Earth. So myself and Eric Chachaferi also stole this term some years ago. At 2.9 gigayear, those are all those points that you saw before collapsed into a mean. You can see we're about 20 C, not too different from present day Earth. And of course, solar insolation increasing through time. And then something happens here. Now, why do I stop at 0.7 in this particular plot? That's because for those of you that know, around 80% of Venus has been resurfaced. There's big fights in the geology community now about when that happened, but the canonical value when I wrote these papers was 750 million years ago. Some people have ideas that it could be much shorter than that, but whether there was one major overturning event, which seems very unpopular now, or many small overturning events, it doesn't matter. The point is something happened, and I can't model my habitable planet in a phase when the freaking planet's turning inside out. Okay, it's not possible. Okay, or did it have a shorter habitable phase? And this thing, something triggered it much earlier on. We don't know. That would be more in line with that Grinspan and Bullock paper I cited earlier on. Okay, so some of these models show it could have been habitable, but there are 3 questions that remain we want to talk about. First is, how long might it have been habitable? So the first is longevity of volatile cycling. What was longevity of volatile cycling? I don't know. But I will say this, I think we should always be a little bit humble about these things. I don't know any geologist today who believes the kind of subductive plate tectonics we have on Earth today are the same kind of plate tectonics we had on Earth 4 billion years ago. But 4 billion years ago, we had volatile cycling on this planet, okay? We were not sitting in an ice house state for the first, 3 billion years of this planet's history, or first 2 billion years of history. There's been volatile cycling on this planet from the beginning. So if Venus had a habitable phase, it probably had some kind of volatile cycling, whatever that was for Earth. If you know what it was for Earth 4 billion years ago, please tell me, because I don't know what it was. And also the water loss. How long was this water around if it was the case that it was on the surface? It's only going to be the Da Vinci mission that really nails that down for us when it flies this mass back into the atmosphere in about 6-7 years that we'll know the answer to this, hopefully. Okay, the second question is what caused what we call the great climate transition? You got to have a great name for your theory. So that's the name of our theory is great climate transition. How did we get from a temperate state to a hot house state? And could it have been through volcanism? So one thing that always drives me crazy when people talk about mass extinction events, they only talk about the dinosaur event. This impactor came and wiped out the dinosaurs. But most extinction events in Earth's history are through volcanism, not through impactors. Impactors are important, yes, but it's really volcanism on Earth that's screwing us over most of the time, not rocks from outer space. Okay, so our hypothesis is that maybe something like an overlapping large igneous province scenario could drive a planet from being temperate to hothouse. And what are these large igneous provinces? These are things like the Siberian traps, millions of square kilometers of volcanism going off at the same time, or the Deccan traps. That's the big fight. Of course, the dinosaurs, the Deccan traps were going off. There was a large igneous province event going off at the same time. And the big fights are between the volcanologists who say they were already on their way out, and the rock people say, no, they weren't. We killed them all off. So, anyway. Okay, so we wrote a paper a couple of years ago. I'm really proud of this little paper. I wrote it with Richard Ernst, who is one of the world's experts in categorizing large igneous provinces, and Jeffrey Scargill, who's a colleague of Mark's and I's from NASA Ames, who I think is one of the world's preeminent experts in time series analysis. So what we did is we looked at the record for large igneous provinces throughout Earth's history. We did some fancy machine learning, blah, 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 Markov chain, Monte Carlo, blah, blah, blah stuff that we did. And we came up with this really nice plot. That's what I want to get to here. And what we found out is, or what we believe we found out, is that there was about a 30% chance in Earth's history that a really large igneous province event could go off at the same time, 2 of them at the same time, a Siberian trap size event, and about a 15% chance that a triple went off. And so what my long-term goals are is to try to model this in RGCM, these kind of large volcanic events, and see, what kind of temperatures do I end up in, and can that drive the planet into a completely different state, and maybe even to a different tectonic state. We'll see. That's long-term research. It takes forever to finish these kinds of things. Okay, so, but if it was large igneous provinces, maybe we can find the remains in the Veritas and Envision radar maps when those came about. Maybe, maybe not. I think probably not, but anyway, you got to be optimistic. Okay, and then the final question, we come back to some of our first slides. Where is this ocean remnant oxygen? What happened to it? Okay, so as I said, I don't think I need to explain this to you all, right? You all know what photodissociation is. You know how this all works. But the oxygen combines with something else is the issue here. It can't escape to space. And how do I know that? Well, there's a really nice paper from Moa Persson and her collaborators in IRF not in Uppsala, they're up in Kiruna, sorry. This is a 2020 paper from GRL, and they say that given Venus's present day atmosphere, Venus could only lost 30 centimeters of water in 4 gigayears by atmospheric escape of oxygen. So you just cannot get rid of oxygen through atmospheric escape. It just doesn't work. It requires removal of it via some other means. And what is that other means? So this is what we hypothesized in our paper, that it was the large overturning events we see on Venus in the current record that was the way to get rid of the oxygen. So you have all kinds of fresh magma showing up on the surface. This oxygen is going to grab onto that, and it's going to end up in the lithosphere. That's the idea. And Edwin Kite, unfortunately or fortunately, tasked one of his graduate students to work on this, and they have a really nice paper explaining how narrow the parameter space is where that works, at least in their scenario. So people are working on it. It's kind of fun. So all of that I've just talked about is all wrapped up in this one kind of picture here. So I'll just go through this very quickly. So we have, of course, we assume a short magma ocean lifetime. Accretion of planetesimals comes to an end. We have some kind of early volatile cycling. We end up in the beginning, we believe that early Earth, and probably in this case, early Venus, would have probably CO2 type dominated atmosphere and eventually move to an N2 dominated atmosphere. We have some kind of event that drives the planet into a runaway state. I think through this volcanism is one hypothesis that works. And then the resurfacing period that comes after that is what pulls the oxygen out of the atmosphere. That's really the only way to make this complicated and confusing model really work, is through all these different processes. But you can imagine a picture for Earth is even more complex than this, as you might guess. Okay, but this habitable Venus scenario still requires water, amongst many other assumptions, as you've seen here. So was there surface water on Venus? Okay. Is there evidence for surface water on Venus? I would say no. There is evidence for water, and that's what I've already shown you from the Pioneer Venus probe, from the Large Probe Neutral Mass Spectrometer in particular. We got this 150 value. Again, when it lost the water and the timescale over that loss, we don't know. But as we're going to see here, that 150 value is not exactly right. Okay, but what was the PV Large Probe Neutral Mass Spectrometer? I love showing pictures of spacecraft, and I think, Mark, this is the last spacecraft we did at Ames before Kepler came along, basically. So this is a really amazing mission. If they flew this thing today, it would be a flagship mission. It would cost a fortune. You just can't believe what this thing had. So first of all, they had an orbiter, which is sitting over there with some people hanging out, guy hanging out here, which had a radar, magnetometer, neutral and ion mass spectrometer on the orbiter. Then it had a bus that delivered these probes. It also included a neutral and ion mass spectrometer, and it took data until 110 kilometers in the atmosphere, and then it burned up. And then 3 small probes that had nephelometers, pressure temp, accelerometer, and radiometer. That's these little guys. And then a large probe on top of everything else with a neutral mass spec, which I'm going to talk about in a second, a gas chromatograph, a nephelometer, and the same thing on the small probes. This crazy thing. Okay, this thing was launched on August 8th, 1978. And you can see here it came flying around, got to Venus. They separated off the orbiter from the large probe. They got into the atmosphere. And they landed in different places. So the orbiter, of course, stayed here. The bus landed right here on the day side. One of the probes was a day probe. There was a sounder probe, a north probe, and then a night probe, basically. These are some really cool pictures that I got when I visited the archive at NASA Ames, which I like sharing with you. So again, showing the multi-probe and the bus and the orbiter. And this is kind of how it happened. Here's the large probe descent. So there was some kind of atmospheric deceleration, 150 to 70 kilometers. The chute deployed at 68 into cloud tops. The chute jettisoned at 46 kilometers, and the impact was about an hour later onto the surface when it stopped collecting data. It was never designed to last on the surface. It was designed to collect the atmosphere in a column all the way to the bottom. This is a cross section. Here's the LNMS over here with its inlet, and the LGC, the large probe gas chromatograph on the other side. This was the assembly of the probe. So Da Vinci is going to be very similar to this in size. The design is going to be very different, but the size of the probe is about the same. It's about 1 meter across, more or less. And I love these lab coats. They've got these super cool lab coats. This is a picture of the flight spare that's sitting at UT Dallas, which I've been to visit a couple times. Those are my fingers, so you know how big it is, the inlet probe there. It's just the size of a couple shoe boxes. It's not that big. It's a picture from some photographs I got at the archive in UT Dallas with the cover taken off with all kinds of crazy wiring everywhere. And this is kind of how the thing works. So again, the multiprobe drops this thing off. December 9th, 1978, 1645. It ends up down here about an hour later. That's our atmospheric gas selection in the cloud layer. Temporary clog of inlets Many people may know about that. There was a clog in the inlets. We believe it was sulfuric acid particles clogging the inlet, not completely, but a lot, and then resumption of intake below 25 kilometers. And these are the basic specs of the machine. So we collected 46 spectra at these altitudes with different kinds of ionization potentials. The mass scale goes from 1 to 208 mass units. There were 232 pre-selected mass positions. So they had to decide what they were going to detect in the atmosphere before they flew. So they knew where to make the measurements at. And the mass resolution was actually pretty good. That's a picture of it at the surface. And these are a few papers we've written on the reanalysis. So we've spent the last 4 years reanalyzing this data. And I have to admit, the reason that we did it was because of this crazy phosphine paper, which you all know about. And we wanted to say, hey, did the large probe see the phosphine signal? No one had looked for it, because why would you? I mean, anyway, so we got the probe data. We were the first people to pull it out of the archive. It was sitting on microfiche. They had to take it out and redigitize it and send it to us and all this sort of stuff. It was quite fun, because all that had ever been published was one altitude point, which I'll show you a little later in the literature. There was nothing else sitting there. This stuff had been sitting in the archive for 40 years. No one looked at it. I'm not saying we found phosphine, but I'm not saying we didn't. It's sort of inconclusive. We're pretty sure we see a phosphorus signal. And the question is, what's the parent molecule? And that we couldn't determine, basically, because there's some isobaric species in there. So this is some of the analysis which is under review as I speak right now. So the Donahue 1982 paper is the #1 point. That's the only published altitude point that they had here at about 46 kilometers. This is a paper from de Bergedal from 91. This is from the CFHT infrared, I think it's a Fourier transform infrared spectrometer in the cloud level here, just below the clouds rather. And this is the trend that we see in the D to H ratio, basically, as we go over. So if you look over here at this plot, this is a little bit more broken out. You can see that the D to H ratio is changing as a function of altitude, something that we don't completely understand yet. But what's really intriguing is that there's some other data points higher up in the atmosphere, and even a really recent paper from 2024, where it's way off the charts. It's way at 110 kilometers. It's a crazy number. It's like 1,500. So we're really confused about what's going on here. So there's a lot of work still to be done to understand what the D to H is saying. Hopefully some modeling and Da Vinci and other things. And we have some ideas, actually, which I won't go into because I don't have time. But I do encourage you to invite my buddy Rakesh Moghul to come and give you a talk just about this. You'll find it really interesting. He's done a lot of work. He's done a great job leading this project. So I'm just going to wrap up here. I have this idea that Venus may have had habitable conditions in early history if it ever had surface liquid water, which we don't know. We really need these in situ observations from Da Vinci to confirm this geologic and maybe even its volatile history. We really need this ground truth from Da Vinci and its imaging. And aside from the fact that Veritas and Envision are going to have radar, they're also going to have infrared imaging. So we'll really be able to characterize the surface of Venus for the first time in a way we never imagined it was possible. And well, I hope that exoplanets will help us inform Venus's early history. I talked about these early magma ocean atmospheres. It'd be great when we can start observing these with some kind of number statistics to tell us what's going on. And certainly these, Earth is the only habitable planet we have in the solar system, and maybe Venus was too. Maybe they'll help us inform exoplanets, whether they're temperate or not, habitable or not, who knows. Anyway, thank you very much.
Questions. I'll also monitor the online chat room.
You're pointing at me?
Yeah.
No, thanks for a very interesting talk. So I'm wondering about this transition to the very hot Venus, and you suggested that it's probably due to volcanism of some sort. But at the beginning of your talk, we were talking about how the high albedo due to clouds is what keeps Venus, maybe in the habitable zone. So am I right in concluding then that the volcanoes somehow make the clouds go away? And if so, why does that happen?
That's a really good question. So we don't know the answer to that. That's what we're working on now at the moment. is to see what they do. But if you look at the work of people like Martin Turbay that's looked at these magma ocean atmospheres, whether they're real, whether they're right or not, the atmosphere itself, the composition doesn't so much matter. But what's interesting is that in their steam atmospheres, they get a lot of clouds on the night side. Okay, so in our case, we don't get that many clouds on the night side. So what happens in a case like that, while you have these clouds doing a great job of shielding, there's nothing on the night side. So the heat just goes out, right? I mean, those of you that have done any kind of camping know how cold it gets at night here on Earth. We have a very short day. But if you look at a slow rotator, where it's sitting there at night, just radiating to space all night long, if you shut that off, the planet's going to start heating up if you trap it. So that's what I think is probably going to happen, is that as we heat up a bit more with the volcanism adding even more greenhouse gases, we're probably going to change the way the dynamics works a bit, and we're going to create extra clouds on the night side and probably trap some of that. But I don't know yet. That's part of a long-term project. These modeling projects take forever to finish, but I hope to have an answer in the next couple of years.
Can I get a quick follow-up?
Yeah.
I was asking about the boss.
Well, ask the boss. Sorry. Yeah.
Please.
Is there an easy way to understand the preponderance of clouds on the day side in those models?
No, it's like I said. I think it's because the Coriolis force is very weak, and so instead of having multiple overturning cells like we have on Earth, you only have one in the north and one in the south, and that in these models creates a very big convective front. And if you have water available at the substellar point, that just drives huge amounts of water vapor into the atmosphere, and you condense out clouds at the substellar point. That is the thing that works here. If you have smaller overturning cells, you'll get some at the substellar point, but they'll precipitate out at the next overturning cell, right? And then you have a lack of clouds. And that's exactly what you see in that Yang picture, where you show all these different bands of the cloudiness and how there are some gaps in there where there's no clouds at all. And in those models, things heat up quite a bit. So it's the rotation rate that really plays the key role in the cloud formation.
All right, I have to think about that.
You can ask me more after, no problem.
Yeah, thank you. This was really interesting. I'm curious about the 5 scenarios that you outlaid for your modeling. How were those chosen as like the representative quantities of water? And is there any indication from what we know about Venus, which ones would be more probable?
No.
Okay.
There's nothing. Because the error bars in the DDH are huge. I also showed you that plot of DDH as a function of height, which is really confounding. So those scenarios fit into those error bounds, basically. That was my idea. I mean, why did I pick them? Because I had to pick something, right? It's a bit like, also in those scenarios for the arid, the 10 meter and the 310 meter, sometimes I get asked this question, well, why do you pick modern Venus topography? Well, it's basically the least worst choice I have. It's what I have. I could pick any topography from Earth history and I'll probably get similar results. So it doesn't matter so much. But what's really fun about it is that when you add this water, unlike on Earth, if you look at Earth, we have a lot of high latitude land, basically, but we don't have a lot of low latitude land. And when you do Venus like this, unfortunately, I don't have a picture of it, but you get a lot of low latitude land and oceans around that, which changes the climate dynamics in kind of an interesting way, because the land tends to have much higher albedo than the oceans, and that also affects the climate a little bit. So that's what we see differences when you look at the mean surface temperatures between the arid planets, the one with 10 meters in lakes, and then the ocean, and then the aquaplanet and the Earth. They're not all the same because it really depends on what kind of surface albedo you have, and it depends on the ocean circulation can be very important. On Earth, sometimes when we take, for example, if we're doing Tally-Lox simulations of an M-dwarf planet and we give it modern day Earth's continental distributions, one of the things that we noticed really early on is that if you put the substellar point of the Pacific, the Americas and Australasia act as kind of barriers for heat transport for the ocean. So this side can be very warm and you have lots of circulation, but the night side, there's no way for the water to transport heat. It's only through the atmosphere, and a lot of heat transport is done through oceans. So your topography matters, actually. The land sea mass really matters. But thank you for the good question.
Yeah, if you go back to your DDH plot,
Yes.
so I seem to notice that the peak in this plot seems to occur where the clog occurs. Could the clog be affecting the Pioneer Venus measurements at this altitude?
Absolutely. You're right. In fact, the Donahue paper from '82 was taken in the clog, basically. And they got the idea that the H2SO4 particle would have some water in it that would dissociate into the instrument. And that's where they got the number form. That's where the 150 comes from, is from that paper. But it's very complex what's going on in this clog. And we have a paper under review right now discussing what happens in that clog and what happens to the stuff that was in the clog as the instrument goes further into the atmosphere, and the stuff in the clog starts to disintegrate and end up in the instrument. And then we find stuff in there that no one noticed before, for example.
Questions from the room? I'll say it again. If you're online, feel free to drop a question.
Yeah, I would say another thing is the Da Vinci people are, of course, terrified about their instrument getting clogged too. And so I've had really struggle with them to figure out, like, are you going to turn on, like there was a paper some time ago where they were going to turn off the mass spec in the clouds because they were afraid of it getting clogged. And it's like, but that's where all the really interesting stuff is. But you know, you got to be careful. You don't want to sacrifice your mission. So it might be, I think one thing to discuss recently is opening up one of the inlets in the clouds. That gets clogged, that's fine. They'll open up a second one after they get out of the cloud. So they don't have to deal with the clog clearing out, basically, later on, which we have to deal with here, in essence.
Other questions from the room? Question about the...
So I guess another thing we don't really know about Venus is rock weathering, but I was wondering, do you try and...
No, I don't. It's a really good question, but no, I don't. There are people that do that, but not us, especially in modern day Venus. That's a really complex subject.
I have a question about the analysis of the large igneous provinces on Earth. So the resultant probability density functions that you showed off weren't super clean.
No.
And is that just because there's not much data on Earth at the timing of these events, or there just aren't that many of those events? Why did they end up so jagged?
There are not that many of these events, and we kind of have to fill them in a way because we only have, we can only measure large igneous provinces globally for about 200 million years, because as you know, the oceanic lithosphere gets renewed about every 200 million years or so. So we have to take the record we have on land and double that. And then we're pretty sure that we don't have the full record either, because we're discovering new large igneous provinces more or less every year. So we don't have the complete record. So, maybe in another 10 years, we could redo the analysis. Might have discovered twice as many, who knows. And also the ones we do have, we'll get better estimates on the volumes. That's one thing we didn't go into too much in the paper was, on the volume component of it. So that's why it's just, we just don't have that much data basically. And there haven't been that many really, really big ones in Earth history that we've measured basically. I mean, the Siberian Traps is the biggest, and there's the Camp, and then there's the Deccan and a few others, but there aren't that many.
And,
Wanna follow up on that?
Yeah.
What causes these?
The large igneous provinces,
Causes these?
there's big arguments in the community about that. We think that they're mantle plumes caused by, what do they call them? LLSVPs, large, low velocity provinces. Basically, they start, I think, at the core mantle boundary, and these plumes come up and they impinge upon it. That's the prevailing hypothesis now, although they use different names. I think there's a new one now. They don't like LLSVP. They call it something else, but that's the idea. They're basically mantle plumes that generate these. But the trigger for them is argued about. It's not clear why they happen and when they happen and why the frequency of it. There's some missing information there that we don't have. We don't know. I mean, we have these, statistics that we put together, but we don't have the full picture. So, I mean, I'm always cracking up when people are talking about, like, what'll Earth be like in 1 billion years? Well, I'm sure that some more of these are going to go off in the next 1 billion years, like a lot. So we won't be around to see how clement Earth is in 1 billion years. Because these large igneous provinces are going to come back again. It's just a matter of when, basically.
philosophical question now related to development. So you talked about the heritage of Rocky 3D coming from Model E. So presumably you inherited a lot of good code, but you also inherited a lot of baggage.
Yes.
And so if you had to do it all over again, would you do it with starting off with an Earth-tuned GCM like that, or would you make some major changes from the get-go about what tools you started with?
I think for us, there probably was no other path because the 800-pound gorilla in my institute is the Earth model. And we share a lot of development with the Earth side of the house. So we're necessarily sort of dependent upon them. I mean, if I got if headquarters gave me, $2 million a year guaranteed for 10 years, yes, I could take a different approach. But I don't live in that dimension of reality. And so I have, my resources are limited. So I have to kind of take this piecemeal approach. There's no way about it. But, that's not to say that we're not ambitious. We always have all these great ideas of things we're going to do, but they always take 2 or 3 times as long as I ever estimate they will. As I'm getting older, I'm getting better about that. But, when you go to your funders, you can't tell them I'm going to ask for money for 3 years, but it's actually going to take me 6 years to do this. We all know that's how the game's played, but that's kind of how you're stuck with, especially with a modeling component like this. It's very difficult.
With that, let's thank Mike one last time.